Welcome back, class. So today we are going to continue our discussion of topics about acids and bases, and we're going to get into today how we look at the amount of hydronium and hydroxide in solution. So how do we characterize whether a solution is acidic or basic, right? So we know that if we dissolve an acid, we create hydronium. If we dissolve a base, we create hydroxide, but how much, right? So we're going to start the idea of trying to quantify these ideas a little bit. And we'll hit on something like the pH scale that I'm sure you're familiar with. But before we do that, we need to introduce this idea called the autoionization of water. So we mentioned already that water is amphoteric, meaning it can act as either a Bronsted acid or a Bronsted base. It can either donate an H plus or gain an H plus, depending on the environment. So what that means, right, is there must be some ions present, right? Because if it's amphoteric, right, and it can do both, then perhaps it can react with itself. And this is what we see, right? We see a small amount of water that reacts with other water. So even in pure water, we have small amounts of hydronium and hydroxide. And so this is what we call autoionization, where water reacts with water to form hydronium plus hydroxide, and of course, equal amounts. Now, again, this is often written as just water dissociates or transitions into hydrogen plus hydroxide, right? Again, we can replace hydronium with the hydrogen ion. We just have to eliminate a water from the other side as well. So that means every aqueous solution always contains both hydronium and hydroxide. What's going to be different is the varying amounts of hydronium and hydroxide. So if you have pure water, of course, these values are equal because every time you generate one, you generate the other. And so in pure water, the hydronium is equal to the hydroxide, and it turns out that their concentration is 1 times 10 to the minus 7 if we're at 25 degrees. So for our purposes in this course, we're going to assume this concentration is good at whatever temperature we're at in terms of, being close to ambient room temperatures, right? When this will vary a little bit, but we're going to assume this value. Okay, so first key idea is that in plain water, pure water, nothing in it, right, we would have hydronium and hydroxide both equal to 1 times 10 to the minus 7 in terms of their concentration. And this is due, again, to the autoionization. There's always a little bit of these ions present. Now, if we were to write out the equilibrium of this reaction, right, in either form, right, the equilibrium constant, right, would be hydronium times hydroxide, or H plus times hydroxide, and that's it, right, because the reactants are all pure liquids. So we're just going to have K equals the products, right? There is no reactants here, so there's nothing on the bottom, so it's just hydronium times hydroxide. And this is what we refer to as the ion product of water. And so if we take pure water and we calculate this ion product of water called Kw, right? So again, this is just the equilibrium. This is just an equilibrium constant for this reaction of H plus, of water in equilibrium with H plus OH minus, right? So the equilibrium for that is called the ion product of water, and it is abbreviated Kw. And so if we take hydronium times hydroxide equals Kw, and if we put in for each of these, so remember the concentration equals 1 times 10 to the minus 7 in pure water. So if I put each of these in as 1 times 10 to the minus 7, 1 times 10 to the minus 7, then that means the Kw equals 1 times 10 to the minus 14th. So the ion product of water is always 1 times 10 to the minus 14th. So in pure water, right, these are going to be equal. But what if we add acids or bases, right? Well, remember, equilibrium constant is still the equilibrium constant. And so if I take hydronium times hydroxide for any aqueous solution, that equilibrium, we have to get Kw, right? As long as we're at the same temperature, or, we're assuming we're at this temperature, then Kw is 1 times 10 to the minus 14th, no matter what aqueous solution is. So the idea is if one of these goes up, let's say we add an acid, so we make more hydronium, then that means the hydroxide has to drop way down, so that the ion product here is always 1 times 10 to the minus 14 for water. And so we refer to these two values as being inversely proportional, right? As one goes up, the other one must go down, so that they're always multiplied to give you 1 times 10 to the minus 14th. And so this becomes sort of one key equation when we talk about acid-base chemistry, is the concentration of hydronium times the concentration of hydroxide must equal 1 times 10 to the minus 14th. So let's start just categorizing solutions. So we've already said they both contain hydronium and hydroxide. If we have a perfectly neutral solution, which just simply means we have equal amounts of hydronium and hydroxide, that means they both have to be equal to 1 times 10 to the minus 7. That's the only way that we can have neutrality, right? Equal amounts of hydronium and hydroxide. If we have a solution that is acidic, that means that the hydronium ion has gone up, and so must be larger than the hydroxide. So hydronium must be bigger than 1 times 10 to the minus 7, and the hydroxide must be smaller than 1 times 10 to the minus 7. So in other words, hydronium is greater than hydroxide in acidic solutions. In a basic solution, it's just the opposite, right? We're gonna have more hydroxide in a basic solution, so the hydronium is going to be less than 1 times 10 to the minus 7. Hydroxide is going to be more than 1 times 10 to the minus 7. So the hydroxide is going to be greater than hydronium in a basic solution. So we can define whether something is acidic or basic based on the value of the hydronium or hydroxide solution. So acidic solutions are always going to have a hydronium greater than 1 times 10 to the minus 7. Basic solutions are always going to have a hydronium ion less than 1 times 10 to the minus 7. And that's how we typically define them, right? We define them based on hydronium ion concentration, which is where we come up with what we know as the pH scale. Now, it was found that looking at things in terms of concentration of hydronium was confusing to people who didn't have an understanding of this, or hadn't, taken chemistry, or hadn't had, a decent amount of chemical background, because you're dealing with these reactions, these equilibriums, you're dealing with really small numbers, right? Everything is minus to the -7, -8, -10, -5, all these really tiny numbers. But we needed everybody, or at least people in all sorts of different walks of life, to understand whether something was acidic or basic in terms of using it, safety, these kinds of things. So we developed, or a system was developed called pH. And pH is just an alternative way to express the hydronium concentration. And we do this by taking what we call the negative log of the hydronium. So it's just simply taking a base 10 log and then changing the sign. And changing the sign ensures that you get a positive value, right? Because if you take the base 10 log of a number less than 1, you're going to get a negative value. And so this just makes sure that our pH values are going to be positive. So if we have a value of 1 times 10 to the minus 7, neutral, right, we get a pH of 7, right? So pH of 7 characterizes a neutral solution. Now, the one thing I need to know to find the pH, right, is this hydronium ion concentration, right? So I need to plug the hydronium ion concentration in to find the pH. Now, what about if you have an acidic or basic solution? So if I have an acidic solution, so remember that means my hydronium ion concentration is going to be a bigger number, right? So when I take the pH, the negative log of a larger number, I'm going to get a smaller value. Okay? So it's going to go from 1 times 10 to the minus 7 to, say, 1 times 10 to the minus 5th. Right? And if I take the negative log of 1 times 10 to the minus 5th, I'm going to get a value of 5. So the pHs that are less than 7 are going to be acidic. And that means those are solutions that have a higher hydronium ion concentration. If you have a lower hydronium concentration, and so the value gets smaller, you're going to get a larger value when you take the negative log. So pH greater than 7 are going to be basic. And as I said, pH 7 is exactly neutral. Now, you can go both directions on this. So while this is one key formula, it's just as important to understand that if I want to find the concentration from the pH, I can do it this way. I can take 10 raised to the negative pH, right? Remember, this is taking the anti or inverse log of both sides. So if I take it's going to be 10 to the x, right, is the inverse log. And so if I take 10 to the x of the pH, and I move the negative sign, so that's 10 to the minus pH. If I take 10 to the log, they cancel out, and I just get what I was taking the log of, or the hydronium. So you have these two equations that we can use together. Now, I know from KW, right, that hydronium times hydroxide must be 1 times 10 to the minus 14th. So what we start getting is these equations that start to work together, right? So if I know one of these concentrations, and I know that the product always has to equal 1 times 10 to the minus 14th, I can always find the other one. And so if I know one of these, I can find the other one. So that gives me a way to get to pH. Or if I know the pH, I can find the hydronium. And if I can find the hydronium, that means I can find the hydroxide. So you can start to see how these equations are going to start to work together. Now, we could see how, how this pH scale makes things quite a bit easier, right? If I can say something has a pH of around 3, right, a lot of these things that we consume, that's a whole lot easier than saying, oh, that apple, has a hydronium ion concentration of 1 times 10 to the minus 3, or 2.1 times 10 to the minus 3. That's much harder to sort of grasp for somebody who doesn't quite have the background than just saying, oh, it has a value of 3. Now, and of course the scale here is 14, right? So pH values go from 1 to 14, with 1 being very acidic, 14 being very basic. Right? And they have to stuck between this range because of that ion product constant, right? That the fact that hydroxide times hydronium must equal 1 times 10 to the minus 14. So there's always some of each. It can go really far in either direction, but we can only go so far. Now, if I have this value of pH, of course, it tells me that something is more acidic, less acidic, right? So the lower the pH, the more acidic. The higher the pH, the more basic. Now, what we need to really kind of understand, now that we've introduced this log idea, we have to understand that because it's a log scale, 1 pH unit, right, corresponds to a 10 times factor, right? And so a small pH change can be a meaningful change in concentration, right? Because if I change half a pH unit, that's changing the concentration by 5 times, right? And so while it doesn't seem like a lot, it's actually a fairly significant change in concentration. So we have to understand that when we move to a pH scale, that we have to understand what a change in pH really means in terms of the concentration of something. And again, range 0 to 14, right? Theoretically, when we get to a pH of 0, that means we have 1 molar hydronium. If we have pH of 14, that's 1 molar hydroxide. Right? Now, you can reach these sort of ends of the scale and even go beyond them, in certain very specified, very unique environments, right, where you get very, very acidic or very, very alkaline conditions. Now, we don't really worry about those in this class, right? All of our stuff is going to be, in this, mid-range of the pH scale, right?